Okay, so hello again everyone, and in today's tutorial we are going to discuss how to include geometric imperfections in ABAQUS. So just a quick introduction. As we know, geometric imperfections, if you have any structural shape, typically we're talking about steel or metallic sections. So these sections, because of the fabrication process, when they are shipped from the fabricator, you will typically have some geometric imperfections, very slight geometric imperfections at both the section level as well as the member level. And these imperfections, of course, are below a given tolerance based on the standards in the respective countries. So these are very small imperfections that most probably are not visible by the naked eye, but again they are there. And these imperfections here, like over here I'm showing like some local distortion imperfections in a typical eye-shaped sections, or like twisting imperfections, or at the member level you could have like out of straightness or out of plumbness imperfections as well. So these imperfections, although they are small, they can affect actually the structural behavior. So they can trigger global instabilities because of these imperfections, or additional forces and stresses in your member. So that's why it is of interest to include these imperfections in our finite element models. So in order to do that in ABAQUS, this is done in two steps pretty much. We are going to go through these steps by doing a quick example right now. So the first step is basically you will need to run a buckling analysis to get buckling modes, which basically modes of deformation, like similar to the ones that we see here. These are results of a buckling analysis. You get different types of modes, global modes, local modes, and so on. And then if you are interested, the second step pretty much, if you are interested in this type of mode, like you want to have this kind of deformation in your actual member, so you will need, in the second step, you will need to scale this spatial deformation profile and maybe superimpose it, but with other modes as well. It doesn't need to be just one mode. You can superimpose a number of modes and scale them, and then import them as an initial geometry in your main model or your main analysis. So this is pretty much what we are going to go through right now using an example in ABAQUS. We are going to model a simple cantilever beam, and we would like to provide like some local geometric imperfections at the fixed end. So we are going to do this in ABAQUS right now. Okay, so now I have ABAQUS opened right now. So let me go ahead and set the working directory as always. So if I go here, let me create a new folder. Let me call it ABAQUS geometric imperfection. Let me use this as my work directory. Then I'm going to say OK. Let me start here. Before I start modeling my part, let me change the name of the model actually. Let me rename this from the default model-1 to model main. You can rename it as you want, but I'll just do that for now. Let me create a part. I'm going to create an eye-shaped beam using solid extrusion, but we can use shell or, well, any kind of section for that matter. So I'm going to say continue. So let me draw here a section. It doesn't matter the dimensions. And that's it. So I have my section. Again, it doesn't matter the dimensions, but this is what I drew for my example. I'm going to use like a 2 meter deep. I'm using millimeter as always and Newton in my model. So here is my section. As always, it's always good practice to do partitions. So I'm going to partition So that's it. So now that looks fine. That looks good. So now I have the part for the property. Let me create just a simple material, steel, and I'm just going to define the elastic part of it. So I'm going to define the elastic modulus 200,000, okay, and Poisson ratio 0.3. I don't need plasticity or anything. This is just an illustration. So just the elastic property will do for now. Let me create a section, homogeneous section. So this is a section for the beam and for using this material. Okay, now let me assign this. So I assign it to my part and done. So that's it. So now we define this. For the assembly, I'm going to create just a single instance for this part. Okay, that's it. I'm not going to rotate it or anything. I'll leave it as it is right now. And then I'm going to the step. I'm going to create a step. So this is, I'm going to call this the loading step. Loading step. So this is static general. It doesn't matter again. This could be whichever step that you are doing. Time period, I'll keep it as 1. This is like 0.1, 0.1. Can reduce this a little bit and increase the maximum number of iterations of increments, sorry. And I'm going to say okay, so that's fine. I have the step. I don't have any interactions, but actually I will go to the interaction module because I want to define a reference point. So I want to define a reference point here at this end, because this end will be my fixed end. So I will create this at the origin over here. So that's it. I created a reference point, and then I'm going to do a rigid body constraint because we mentioned that. So this is constraint fixed end. We mentioned that it's always better to apply things using the reference point instead of applying things to surfaces or like boundary conditions or load. So I'm going to select those. So that's it. I have a rigid body here at this end. Let me create another point as well over here. So this would be 0, 0, and in Z that will be 2000. So I have here another reference point. And let me create another restraint. So this is call it the free end. So this is where I'm going to apply my load or displacement. I'm going to select that. Let me edit. Let me reselect the right reference point. And let me reselect here the edge. So I'm going to select this edge. I'm going to say done. That's it. So I have the 2 reference points. Now I go back to my load. So I'm going to create a fixed end. So I'm calling this fixed boundary conditions. So this will go from the initial step because these are fixed boundary condition. I can use the symmetry or the displacement, it doesn't matter. I'm going to select this point, done. I'm going to block everything. This is a fixed end, that's it. And then for the displacement, well, pretty much I'm going to apply a displacement at this part over here. So this we can apply something like that, create boundary condition, beam displacement or something. And then this can be applied in the loading step. Then I'm going to select this point. And I'm going to lock everything pretty much. And I will only leave the axial displacement free. And for the displacement in the y direction, I'm going to apply like something like, let's say 100 millimeter or something like this, using the ramp amplitude. I'm going to say, okay, that's fine. So now let me go to the meshing. Well, it's straightforward. Let me check. Let me select the part. Let me check the mesh size. So perhaps I can use like 15 or something. That looks That looks fine. I'm going to say okay. Then I'm going to mesh it. Yeah, so the mesh looks okay. So that's it. So now the only thing remaining is to run the job, but of course we don't have imperfections yet. So we need to add imperfections. So how we can do that? Okay, so now we have our model. Let's save it. So I'm going to save my model and call it GI, Geometric Imperfection Tutorials, tutorial. Here we go. And then what I'm going to do, I need to conduct buckling analysis. As we mentioned, the first step, we need to conduct buckling analysis actually. So I'm going to take a copy of my main model. So I'm right click on main model. I'm going to say copy model. And then I'm going to name this model buckling. You can name it whatever you want again. And then let me go to this model buckling here. And I'm going to modify things. So right now I'm in model buckling. This is the model that I'm currently in. I'm going to go to the step. I'm going to delete the loading step actually. And I'm going to create another step. I'm going to call this buckling step. All right. So the buckling step, I'm going to select the procedure type. I'm going to select linear perturbation. And then I'm going to select buckle. I'm going to say continue. And here I need to specify the number of eigenmodes that I request, basically the number of buckling mode that I request. So let's say I just need 5 or something. I don't need more than that. And here this is for the maximum number of iterations in order to obtain these eigen values. Typically this is a very standard geometry. It's not a very complicated model, so there wouldn't be any problems trying to iterate to find these eigen values. But in general, if you want to be safe, you can increase these numbers in order to help the program find or obtain these eigen values. I'm going to say okay, and that's it. So now I defined my step, the buckling step, and I go to load. Right now I'm not going to apply. Right now we have the boundary conditions, the fixed boundary conditions. That's all right over here. And what we will need in buckling analysis, in order to conduct a buckling analysis, you need to create a reference load. So the buckling modes that you are going to get will depend on the kind of load that's going to be applied on this beam. So you need some kind of reference load in order to obtain these buckling modes. So in my case, I want to create a reference load, which is basically a load here that acts in the y direction at this free end. But it could be anything. You could apply it like axial load on the beam, or if you want to trigger torsional modes, you could apply a torsional moment at this end. So you can apply any kind of reference load in order to trigger the buckling modes that you want to see. So I'm going to select here in create load. I'm going to call it reference load. And this will be applied in the buckling step. I'm going to use concentrated force. I'm going to say continue. I'm going to select this point. I'm going to say done. And I'm going to apply, again, this is up to you. You can apply this an axial reference load. It doesn't matter. The sign, it doesn't matter. Again, this is a reference value. So I'm going to say here just 1. I'm going to put a unity, like just 1 value in the y direction. So it doesn't matter this value. So essentially at the end, once we get the buckling modes, you are going to get the eigenvalues. And the eigenvalues represent the buckling load of this corresponding to this buckling mode. All right. So if we take these eigenvalues that will appear after we do the analysis, if you multiply those by the reference value, then you get the value in kilonewton, or in Newton, sorry, in our case. So that's why I put here unity, like you don't need to put something different. So I'm going to say okay. So now I have my reference load. Again, it doesn't matter the direction. And that's it. If I want to put a reference load, I could have put a reference load like a compression on the column so that I will get some modes that are representative of the compression. So that's it. And then I just need to go to the job. I'm going to go to the job manager. I'm going to create a job. I'm going to call this job buckling. And this is based on the model, the buckling model that we created. I'm going to say continue. I'm going to say okay, and then I'm going to submit. Hopefully we have defined everything correctly. So this shouldn't take any time. It should be very, very fast. So now it's running. There are no iterations. It's like just one shot. And then it shouldn't take a long time because this is a very simple model and we only requested 5 eigen modes. So now it's running, and now actually the analysis completed. So I can go to the results. So if I click on the deformed shape, so now here you are. So now you see the deformed shape. So this is mode number 1, and the eigenvalue is 30027. So this value, negative value, so this means it's in this direction. So multiply this by the reference load, which was 1. So this gives you the value in Newton. So this is basically the eigen or the eigenvalue or the buckling load that would trigger this kind of mode is 30 or negative 30 kilonewtons. So 30 kilonewton in this direction. So this is the first mode. Maybe I can fix a little bit the scale of the deformed shape because it seems that it's very, very large. So I can make here fix the scale factor because it seems like exaggerated too much. So maybe I can do this 20 or maybe 50 or something. Yeah. So here you go. So this is the buckling mode. Buckling mode 1. It's a local buckling mode, as you see here, which this is something I would expect it because this is the fixed end and I'm applying the reference load like this. And then if I go to the next, so this is mode number 2, which is pretty much similar to mode number 1, but in the opposite flange. That's why you have the same value for the eigenvalue, but it's a positive value instead of negative value. So again, mode 1, mode 2, and then if I keep going, these are mode 3, mode 4, mode 5, and then we pretty much didn't request more than that, but if you requested more, then you are going to see the other modes. So this mode, this is mode 5, this is less probable to occur, all right? So the critical ones are mode 1 and mode 2. So let's say in our model, in our main model, we want to pretty much consider these kind of imperfections. So if I look in the here in this YZ plane, so I want to consider these imperfections in my main model, and I want to do this in both the top flange and the bottom flange. So from mode 2 you get the buckling in the top flange. From mode 1 you get the buckling in the bottom flange. But you see here, this buckling here, it opens up downward, and this one over here, it opens downward as well. So if you want it to be symmetric, so pretty much you want to change the direction here of mode 2. So we are going to do this by specifying a scaling factor in our main model. Okay, so these are the two buckling modes that we want to consider in our model. And again, these ones, you can see here the displacement. So you have here the displacement. So the displacement, it says that the peak of my buckling wave is 1 millimeter. So this is the peak over here is 1 millimeter. So in my main model, if I'm targeting a specific value or magnitude of this geometric imperfection, if I want this imperfection to be 2 millimeter, so this means I want to scale this buckling mode by 2, right? If I want this, the peak of my buckling mode in my main model to be 5 millimeter or 5.5 millimeter, then this means I need to scale this buckling mode by 5.5 and so on. So that's it. So the thing that we need to do is to go to our main model and tell ABAQUS that we want to export this buckling mode shape or this deformed shape, and then I want you to scale it by this much and add it to my model. But before we do that, we need to do something else. So right now in our analysis, if we go to the directory where we ran the analysis, we need to have an output file that saves this geometric deformed shape. So in order to generate this file, we need to do something in our model. So we need to specify, we need to tell ABAQUS to create this output file that stores this imperfection, or pretty much the deformation coordinates of all these mesh elements during the analysis. So right now we don't have this file. In order to generate this file, you need to go to the model, the buckling model. You need to go to edit keywords, and then you need to scroll all the way down. And then you need to modify the input file by adding a new command. And this command goes like this. You do an asterisk, then you say node file, then comma, then you say global, then you say equal no, then you say comma, and then in the next line you need to specify mode. You say mode equal to 1, comma, last mode with a space equal to whatever the number of last modes. So this is pretty much, I'm telling ABAQUS that I want to create a node file, and I'm going to use the coordinates of my principal axis, which are the ones here, which in our case are the same as the global axis anyway. So this is the global coordinates, sorry, that we are going to save these values of these deformations. And I'm going to write all the deformed coordinates of my model from mode 1 to mode whatever. So in our case, I don't need all the modes. I just need from mode 1 to mode 2. And then I'm going to say comma again. And then in the next line, I'm going to specify what kind of data or node field variables you want to save. I'm going to save U, which is the displacement. So that's it. Pretty much you need to include this to write it in your input file all the way at the end. So again, you can specify the exact number of modes, or you could say here for the last mode you can say 5. It doesn't matter, because later on in the main file we are going to tell ABAQUS that we want exactly mode 1 and mode 2. But here I don't need to write all the deformed shapes of all the modes. I just need mode 1 till mode 2. And then I'm going to say OK. And then I'm going to go again to the job, and let's rerun the analysis. Before I do that, let me go to my work directory so that we observe. So right now this is the analysis that we conducted previously, and I don't have this output file. So what I need to do now is to pretty much resubmit the analysis. And if I resubmit the analysis, so right now you see I have the files are being generated for the analysis. Sorry. So we are getting an error. Yes, I think the keyword, we did a mistake when we wrote the keyword. So let me check this again. Edit keyword. Yes, the mistake that I did, I shouldn't put a comma over here after last mode equal to whatever the number. I shouldn't put a comma here. So let me click OK again. And let me resubmit. So now if I submit it, let me look again at the output. So now we should see this .fil file. So here it is. So this file over here, .fil. So this is the file that we wanted to generate, and this file pretty much contains all the deformed values of my model. So that's it. We concluded this analysis. So the only thing now that I need to do, I have the .fil file. So now I will go back to my main model. So if I go back to my main model, what I need to do, I need to tell ABAQUS now that I want to add these values. All right, I need to get these values that I already generated from the buckling analysis as initial geometric imperfections. So I need, again, this I cannot do from the interface. I need to do this using the keywords. So I will click on the main model. I'm going to say edit keywords. And then I will scroll over here, and before the step section, before the section that defines the step, over here I need to add my command. So the command will be asterisk and then imperfection and then a comma, and then I'm going to say file equal to, and then I need to specify the name of the file that has this data. So if you remember, we called this job, we called it job buckling. So I'm just going to specify the name like that, and then I'm going to say comma, and then I'm going to specify the number of the step. So this is the step of the buckling analysis that we, because in the job buckling, this job that we created, there might be multiple steps. So I need to tell ABAQUS here which step exactly. So this is step 1 because we actually didn't create more than one step. And then in the next lines, I just need to specify the number of the mode and comma the scale factor. So mode 1, I'm going to multiply it by, well, whatever number that you want. So I can say, for instance, multiply it by a scale factor of 1.5. And then for mode 2, in my case, I want to multiply it by negative 1.5 because we said we want the buckling peaks in the flange to be symmetric. So you can add whatever you want. You can add whatever you specify, whatever the number of modes and the appropriate scale factor corresponding to each one. And once you're finished, that's it. You are done. All right. I will actually increase here the scale factor so that it becomes visible in the actual model. So let me put this like 10. I'll make this like 10, scale factor of 10. And then I'm going to say OK. And then let me go to the job. And then I'm going to create a new job. I'm going to call it job loading, my main job pretty much. That's fine. And I'm going to submit. Okay, so it finished. It doesn't matter. I only need, I can actually need like just increment 0 just to show this. So let me look at the results, and I don't even need to show the deformed shape. As you observe here, so this is my model, and this is at, if I go to step 0, like increment 0 over here, you can observe that the imperfections were imported correctly. If I look in the YZ direction, so you see here, now I have a buckling, an initial imperfection in my model, in the top flange and in the bottom flange. So now I can make sure that this has been imported correctly. So now you see how does it look like. Of course, if we put the correct scaling factor, this will be very, very small, so it might not be observable. So that's why if you want to make sure, perhaps you can assign it a very large scale factor in the beginning just to make sure that it's working correctly, and then you can modify this later on. So that's it. This is how you include geometric imperfection based on buckling analysis in your model.